So, hello everyone, this is your course instructor Khushwant Fatnani. Let us start off with the session. Like always, we'll always start with a short prayer and meditation session. So, request all of you to please join your hands, close your eyes, and join me in the short prayer and meditation session. Eyes closed, smile on the face. Three counts, one by one. Deep breaths in and out. Deep breath in and out. Let your face be glowing with a smile. Once again, take a deep breath in and a deep breath out. Once more, breathe in and breathe out. Let's pray. I'll request you all to pray at your ends. Allow your ears to hear the words of your mouth. God says, one of the scriptures says that ask and you shall be given. Sometimes in life, we have to ask for what we want to get or achieve. Let us start and give thanks to the God. Dear God, I thank you for good health, wealth, and wisdom. I thank you for all the love, for such good support, mentorship, love, and respect from my family members, friends, and mentors. Dear God, I thank you in advance that I have cleared JEE Advanced 2020 in flying colors and have got admission into the best of IIT of my dreams. Dear God, I thank you that I've cleared NEET 2020 and got admission into the best college of my dreams. Thank you in advance. Thank you. Thank you. Slowly and steadily, with a smile on the face, you may open your eyes. So, with this prayer class, let's begin. So, I will want, one by one to each one of you to help me with where we were and what we were doing. If I can recall, we were doing the assignments, right? We were on assignment number 10. So, let us continue with the same. The discussion of the assignment number 10, we are on question number 7 of the assignment. All right. So, Atul, can you please read the question for us? Yes.
Yes, sir. I said minus 20 degrees Celsius is added to 50 gram of water. Is added to 50 gram of water at 40 degrees Celsius. When temperature of mixture is found to be 0 degrees Celsius, the 20 gram of ice is still unmelted. Take specific heat of water equals to 4.2 joules per gram per degree Celsius. Specific heat of ice equals to 2.1 joules per gram per Celsius. Specific latent heat of fusion equals to 334 joules per gram at 0 degrees Celsius. How much ice was added?
Great. So, class, we have been given that we have 50 grams of water, right, being added to some ice. We don't know that value of or the mass of ice. We need to find it out, right? 50 grams of water is being added such that it is at 40 degrees Celsius, right, to the ice. And we see that after some time, the mixture attains a temperature of 0 degrees Celsius and the amount of ice left is 20 degrees Celsius. This is the amount of ice left, right? Okay. So, class, what is the question trying to tell us? That, right here, we can have something very like beautiful to understand. So we have, let's do a mass balance first, a simple mass balance. Initially, let's say ice was m grams, water was 50 grams, it's given. So what will be the water which is left finally? Let us conserve the mass, right? So according to mass conservation, we will have m plus 50 is equal to 20 plus, let's say this amount of water left at the end is x, right? So it will be given as x is equal to m plus 30 grams, right? So we can take this as m plus 30 grams, right? Okay. Atul, would you like to suggest any way to solve this question, any approach? Yes, Atul.
No, sir.
Okay. So class, I'm telling you one very beautiful approach in order to solve any such question, right? So have a look at it and I'm sure you all will understand that how to solve this question if it comes from any time later, right? So this is, see, this is how ice melts, right? A very beautiful concept. So whenever ice melts, this is how it melts. So initially, let's say ice is at a sub-zero temperature, let's say minus 20 degrees Celsius. Okay. Now let's say we start heating it or it starts absorbing heat. So what will happen? Its temperature will rise. Whenever temperature rises, the amount of heat which is absorbed is given as mc delta T, where what is m? M is the amount of ice that melted, Ci is the specific heat capacity of ice, and delta T is the rise in temperature. Let's say this ice has a temperature now equal to 0 degrees Celsius. Please jot this down, class, in your notes. Now what happens is called as phase change, and the amount of heat which is absorbed is called as latent heat. So actually, heat in any substance, class, is absorbed in two ways. Heat is always absorbed or released in two ways, right? Heat is absorbed or released in two ways. So one is called as sensible heat, whereas the other is called as latent heat. Sensible heat means the heat which contributes to rise in temperature. Sensible heat is the one which contributes to rise in temperature. right? Whereas latent heat is the one which causes change in phase, that is change of phase or state. This is how the two different values of heat are categorized. So this is given by m into c times of delta T, that is mass into specific heat capacity times of change in temperature. It can be rise, it can be fall, depending upon whether the heat is absorbed or released. Similarly, the ice which is similarly the heat which is connected with the change of phase is given as mass times of specific latent heat, right? Or latent heat capacity. So that is given as M into L, where L is specific latent heat or latent heat capacity, right? So class, have a note of this also. Now, according to this definition, initially first there is a change in temperature, a rise of temperature in ice from -20 to 0. Then what should happen is there should be a phase change, right? And the phase change should be in a way that this ice should melt in order to form water, right? So let's say this was Q1 and let's say this should be Q2, correct? Now, this is how we categorize things. Now, let us talk about water. What happens to water? So let's say water was 40 degrees Celsius, right? At 40 degrees Celsius. Now, this water also loses some heat, right? And it must have given it to ice. So let's say it loses the heat given by Q3 is equal to, again, its mass into specific heat capacity of water into change in temperature in water. And now the temperature of water becomes 0, right? Generally, we see in most of the questions, water when it comes to 0 degrees Celsius, it tends to be there, right? It does not go to a sub-zero temperature. Generally, if it goes, like if there is sufficient amount or sink for heat of water, it will also convert into ice. That is not an issue. But then in most questions, it does not, right? So let us try to see that what happens for our case, right? So in our case, we have, see here everyone, we have ice is first of all turning from -20 to 0, right? So this is of course there, but then not all the ice is converting into water, right? Not all the ice is converting into water. Only some amount is converting, right? Let's say m minus 20, because initially we had m. Finally, what is left is 20 grams. So definitely m minus 20 grams got melted. I hope you all are clear with this, right? That initially there was m grams of ice. Finally, if 20 grams is left, it means m minus 20 grams of ice got melted, right? So what you're going to do is write this expression of heat. So there is a principal class which is called as principle of calorimetry, which we had seen in the last class. Principle of calorimetry. So this principle says us that amount of heat lost by one substance is equal to the amount of heat gained by another substance if they are placed in close contact and there is no loss of heat. I'll write it here. When there is no dissipation of heat, when there is no dissipation of heat, the amount of heat lost by one body is equal to amount of heat gained by another body. So this is what the principle of calorimetry says. Now let us apply this principle here. So what is happening in our case? In our case, ice is water is losing heat and giving it to ice, right? So the heat lost is by water, right? And how much amount of heat it loses? See here, class, right? So it loses a heat of, let's say it was at 40 degrees Celsius, so it turns to water at 0 degrees Celsius. So we have for water, Q3 amount of heat is lost, right? And that heat is gained by ice, right? Given, which is given by, which is given by first ice absorbs some heat. So this was for water, right? Then the second one, the first part is amount of heat which is absorbed by ice for rise in temperature. Second part is the amount of heat which is absorbed by ice for a phase change, right? So we will write that this part is by ice. Class, if this content is clear to you, right? If this content is clear to you, what I have written on first page, please raise your hand. Yes, class. Okay, great, great. Thank you, class, right? So I think you understood that what is happening in our case, heat is being released by water and that is what is being absorbed by ice, right? So now in our case, what we'll do is just put the values in the expression, right? So we have Q3, that is the amount of heat which is released by water, is given by M, that is, let's say MW, the mass of water, into specific heat capacity of water, right, into delta T for water. Similarly, let us substitute the values of Q1 and Q2. Q1 is the amount of heat which is gained by ice as its temperature rises from -20 to 0 degrees Celsius. So we have M ice, C ice, delta T ice, plus next is the amount of heat which is absorbed by ice when its temperature is constant but its phase changes from ice to water. But please mark, class, that not all ice is melting. Only M minus 20 grams of ice is melting, right? M minus 20 grams of ice is melting, right? So if this was M ice, right, only M ice minus 20 grams is melting, right? And we have the expression as L into Mi minus 20, right? I have just substituted the values which we had learnt in the last expression. Now, or which we had seen in the last expression. Now let us take the values. So the water, right? The amount of water is given in the question as 50 grams. So we'll substitute instead of MW 50. What is the specific heat capacity given in the question? The specific heat capacity for water given is 4.2 joule per gram. So we'll take this as 4.2, right? And how much is the fall of temperature in water? From 40 it comes to 0 degrees Celsius, right? So we'll have 40 minus 0 degree Celsius, okay? Then amount of ice, this is what we want to find out, mass, right? So we have taken this as M. Now specific heat capacity of ice is given as 2.1. So we'll take this as 2.1, right? Now, how about the change in temperature? See here, the ice was at -20, it came to 0, right? So the change in temperature is 0 minus -20, correct? Then plus of L times of M minus 20, right? I hope until here I am clear to everyone. So this expression, just solve it class further. Let me know what you get. Yes, get going. Yes, class, get going. Let me know what you get as the answer. Just raise your hand, right, once you're done. Yes, class. Right. So see here, class, that the expression as we'll have the expression as we have 50 into 40, right, into 4.2. That gives us 8400 minus is equal to, so we have other on the other side the expression is 2.1 into 20, right, which is nothing but 42 m plus 20, pardon me, m into l, sorry, m minus 20, and the value of l, let us substitute this value. It's given as, I think, 334, right? 334, right? So we'll have 8400 is equal to 42m plus 334m minus 6680. All right. Therefore, we will have 8400, right, plus 6680, which will give us 15080 is equal to, we have 42 plus 334, which gives us, I think it should be 376 into m, right? Let us divide this expression. So whenever you have such expressions, class, it is not necessary that you find out the exact value. You can find out an approximate value, right? An approximate value, not the exact value. So I'll tell you the options in the questions. Choose one according to this, right? Let's say you have the options as 40, 50 grams. All these are in grams, okay? 40 gram, 50 gram, 60 gram, or 100 grams. So the answers are quite far away. So if you take some general approximation, you'll easily get the answer, right? So try it, class. So see, I can at least sense one thing, that we have this expression as nearly 15,000, right, whole by 375, right? So let me take this as 400, or let's see, if in case I take this as 400, what I'll get. So I am increasing the denominator, right? That is, I'm decreasing the entire fraction. So the value should be a little greater than this, a little greater. Let's see. So we have 150 by 4, right? Which is given as 37.5, right? So the answer should be nearly something greater than 37.5, and it cl closely matches the option number A, right? So I'll get the answer as 40 grams, right? Class, in case you could get how I have assumed the answer and how I've made this calculation possible, right? Please raise your hand. Yes, class. Right? If my assumption is clear to all of you, how did we go about it? Please raise your hand. Yes, class. Okay, great. Thank you all. You can bring your hands down. So this is how we solve this question, right? All we have to do in all such questions is that take this understanding home, right? That what is happening to ice, what is happening to water according to the data given in the question, and then substitute the ice water connection, right? How, which one is losing heat, which one is absorbing heat, how do we equate them, right? So Atul, are you clear now with the question?
Yes, sir.
Sure.
Yes, sir.
Can you briefly explain what did we do in this question? Yes, get going.
So, in the question, sir, water is added to some amount of ice at -20 degrees Celsius, and
Uh-huh.
its temperature changes to 0 degrees Celsius.
Mm-hmm.
And then we will use the principle of calorimetry as amount of heat lost by the body is equal to the amount of heat gained by the body. So,
Uh-huh. Right. Absolutely correct. So,
so the temperature of the ice changes from -20 to 0 degrees Celsius.
right.
So it is sensible. It is sensible heat. So we will
Very
use
good.
the formula as mc delta t for conversion of ice to ice at 0 degrees Celsius.
Right.
Then then it changes from then it then phase change occurs. So we will use latent heat formula,
Right.
that is delta q equals to ml,
Right.
and we will equate the initial heat to the final heat. So we will get the formula as mc delta t for water equals to mc delta t for ice plus ml for water, and the remaining mass of water, the melted mass of water is m ice minus 20.
Absolutely correct. Absolutely correct. Absolutely correct. Great, great. Atul, it's clear, right? Clear to you everything
Yes, sir.
whatever we did, right? That the amount of heat which is going
Yes, sir.
from water, that is actually the same amount of heat which is being absorbed by ice, and that ice absorbs it in two parts. In the first part, it absorbs this as sensible heat, right? That is which is utilized for the change in temperature. Then it absorbs this heat as latent heat, right? That is at a
Yes,
constant
sir.
temperature, but
Phase
causes
change
phase
occurs.
change,
Different phase.
right? Rise at different phases. Great,
Yes, sir.
great. Thank you, Atul. Right. Okay. Now,
Yes.
class, let us do question number 8. It is very similar to what we had read last time. So, Karuna, can you please read the question for us? Yes, Karuna, get going.
Yes. Ice at -20 degrees
No,
Celsius
no,
is added.
this one is
Oh,
done.
sorry.
Question number 8.
Yeah, sorry.
No worry.
Uh, equal equal rods of length L and area of cross section A each are connected as shown in the figure.
Uh huh.
The figure is like a box.
Uh huh.
Yeah.
What next? Yeah, tell us.
The temperature difference between AD is 100 degrees Celsius.
Okay, so let
Calculate
us draw
temperature
class.
difference.
Let us draw this. What Karuna is saying. We have we have different rods, each of length L, right? So this is L, right? This is L, and this is again L, right? All of them are of the length L, right? So maybe we can just give the length of one, or maybe together all for all of them like this. So just naming them here. This entire length would be 3L. This is L. This is also L. Now we are given with some points like A, B, C, D, E, and F. Right. Apart from this, we have been told that they are equal rods of same length and area of cross section A. Okay. Yeah. Get going. Is the temperature difference between?
Difference between A and D is 100 degrees Celsius.
Mm-hmm.
We have
The
to find the temperature difference between B and C.
Okay, so the temperature difference between A and D class is 100 degrees Celsius, right? So delta theta, right? Let's say here if the temperature is 100, right? The temperature at this point is 0 degrees Celsius, let's say. Now we are being told find out the temperature difference between the ends BC. Let's say we have to find delta theta BC. This is what needs to be found out. Okay. So Karuna, what do you think should be the approach to solve the question? Have we read some concept in this regard? Yes, Karuna, get going.
Oh, yes, sir.
Yes. Try it out. Try how should we go ahead with the question? What do we need to find out what is given? Yes.
We are given that the length of all rods are equal and
Yes.
area of cross section is equal.
So what does that tell me? If I can convert this graph into, or convert this figure into that of resistance,
Resistance.
right? We can do this, Karuna.
Yes, sir. Yes, sir.
Right. So we'll have, let's say, each of these three rods, AB, BC, and CD, represent three resistors, right? AB, BC, and CD, right? Then again we have three more rods, right? Or we can take it one rod of length 3L, whatever. Is the diagram correct, Karuna? Just verify it.
Yes, sir.
Okay. Now, how can we give, if the resistance of each is R, how can we give R, Karuna?
For
What is the formula
AB,
for R? L upon
L upon AK.
AK, where what is L, Karuna? L is the length, right?
Length.
What is
A
K?
is cross section.
A is area of
K
cross
is,
section. Yes,
yeah,
area of cross section. Okay.
K is thermal conductivity.
K is thermal conductivity. Absolutely correct. Okay. Now, how can we go about it after this?
So we can equate the resistance of the A efficient with,
Let's understand this, right? That what is happening in this question, you're absolutely correct that we can do something with the resistance. We can find out the effective resistance, right? And we can also see that how is the temperature taking place between BC, and how is the temperature taking place between A to B, right? We can have a look at that before we proceed. Correct? Something like this,
yes, sir.
right? Think more about it. Think more. I'll give you some more time. Think more. How can you find out the delta theta? Can you imagine this condition in terms of electric current? What happens if a current enters the point, let's say over here? So let's say I'll represent a red color line to represent the current. Karuna, what happens if I current enters the end A? What will happen at the end junction B? Will it just keep moving, or will it distribute?
It will distribute, sir.
Distribute, sure.
Yeah.
Right. So here, let's say we have I current which enters the end A. So it will distribute into two parts. One will go below and one will go travel ahead. Right? Something like this. And then
Yes, sir.
again, both will meet up at the end or at the junction C. Right? Here they got distributed. Here they meet again and again travel as the current I. Am I correct in this understanding, Karuna?
Yes, sir.
Right? So first, as you said, let us find out the effective resistance of the circuit. Effective resistance of the circuit. So we can see that the circuit can be resolved in a manner. First, the central one, these three which are resistances below, between A, sorry, between B, E, F and C, right? B, E, F and C. What can be the net resistance in this zone, Karuna? R plus R plus R, right? Because they are in series.
Yes.
Because they are in series,
Series.
right? So we'll have this as 3R. This is R. This is also R. This is also R. Okay. Now let us go for the next part, Karuna. So now we can take this as R, some other resistance, and then some other resistance, right? So this will be R, this will be R. What will be the effective resistance of the central zone? Let's say R dash. The central resistance R dash is equal to R into 3R whole by R plus 3R, right, Karuna?
Yes. Yes, sir.
So that will give us 3R squared upon 4R, which is 3R by 4. Can we write it this way, Karuna? 3R by 4. Is it correct?
Yes. Yes.
Write it.
Yes, sir.
Okay. Now let us even reduce it further. So the, like, simplify the circuit further. So we have 2R plus 3R by 4, right? So you have 2 plus 3 by 4, right? That is 2 into 3 by 4. So we have 2 plus, that is 2.75, right?
Yes, sir.
So we'll have this as 2 3 by 4 r, right? Or we can also call it as 2.75 r or 11 by 4 r, right?
Yes, sir.
Now that we have this answer, this is the effective resistance which we were looking for. So we have effective resistance R effective given as 11 R by 4. What next, Karuna? What do we have to do further of it?
So we have to equate it to the above circuit.
Yes, so we can see, let's say we have I naught current is going here, I1 current is going here. So what can we write? We can write that the current I, right? The current I is equal to I naught plus I, right? I1, I naught plus I1. Can we write this here,
Yes,
Karuna? Because this
yes,
is
sir.
the same current which is distributing, right?
Yes, sir.
Now, how do we relate current, heat current, and the temperature difference, Karuna? Do we have a relation between them? H is
Yes, sir.
equal to Ka by L into delta theta, right?
Yeah.
Or we can
Yes, sir.
also write this as H is equal to delta theta upon R, where R is L by Ka,
Yes, sir.
right, Karuna?
Yes, sir.
So we'll have, instead of H, we will substitute I, right? So, or instead of I, we will substitute this value, right? So I is because of net current is because of net delta theta, right? Upon effective resistance, which is equal to the, okay, for I naught, Karuna, for I naught, what is the temperature difference that we can take? Let us take this as theta. How much? Theta, right?
Theta.
is
Theta.
is
Yeah.
this not the same temperature difference which is for which is causing I1 to flow? So we have one thing, Karuna, that whenever heat current is flowing, it is because of some temperature difference. Am I correct? Whenever heat current is flowing, it is
Yeah.
because of some temperature difference, right, Karuna?
Yeah. Yes, sir.
So in this case, I naught is flowing because of temperature difference between B and C. I'll repeat,
Yes,
I
sir.
naught is flowing because of temperature difference between B and C, correct?
Yes, sir.
Similarly, I1 is also flowing between B and C. Can we see this, Karuna?
Yes, sir.
So if the temperature difference between B and C is equal to theta, how can we write the expressions here of I naught and I1 in terms of theta? Theta upon, right, R naught plus theta upon R1. Am I correct, Karuna?
Yes, sir.
Right? So we'll write first of all the net temperature difference. What is the net temperature difference between A and D, Karuna?
100 degrees Celsius.
100 degrees Celsius. We can also take this as first the temperature difference between B and C is theta BC, right? So we have this net temperature difference is nothing but the temperature difference between the ends A and D whole by R effective is equal to temperature difference between BC upon R, which R I'm talking about RBC,
R.
right?
RBC.
RBC or R naught, and sum of this with theta between again RBC, because I1 is also flowing in the same route, whole by the resistance between B, E, F, and C. We have taken this as R1. That is this resistance. So, class, I would like to let you all know that this is equal to R naught, because this is B, this is C. Whereas the one which we have taken as R1 is equal to 3R. Right, Karuna?
Yes, sir.
So we'll substitute the values. So we have temperature difference between A and D is 100, right? R
100.
effective we found as 11R by 4. This is equal to temperature difference between B and C needs to be found out. So we'll take it common. 1 by R naught. R naught is nothing but R, right? And R1 is the temperature difference between again, sorry, R1 is the resistance between B and C, but this path, this part, this entire part,
3R.
right? Which is 3R. Absolutely correct, Karuna. Absolutely correct. So we'll have this as 3R. So therefore, we'll write theta BC is equal to 400 by 11 R in the denominator, right? And this will become 1 plus 1 by 3 will be 4 by 3, right? This is theta BC 4 by 3R, right? So we have 3R here in the numerator, 4 in the denominator, right? So this will give us I think 100
300
into
by 11.
3 upon 11. 100 into 3 upon 11, that is 300 by 11. Am I correct in writing this?
Yes, sir.
Okay, just go through the question once again, Karuna. Be sure that you have understood this well, right? I think this should give you somewhere around 27.27 Celsius, right? Okay, so Karuna, once you're sure with the approach I have adopted in the question, let me know. Are you clear, Karuna?
Yes, sir.
Properly?
Yes, sir.
Okay, can you please explain the question and the solution both to the class? What is given, what is being asked, right? What is being asked, and how do we find it out? Yes, Karuna, get go.
Yeah, given is that
Just
all the rods are of.
yeah, I'll use this delta theta expression over here. Yeah, yes, Karuna, get good.
Yeah, we are given that there are uh, 6 rods of
Mm-hmm.
same length and cross section arranged like in the diagram, shown in the diagram.
Mm-hmm.
The temperature difference between A and D is 100 degrees Celsius. We have to find the temperature difference between B and C.
Absolutely correct.
So we have converted the diagram into a resistant form,
Mm-hmm.
and we know that resistance is L by Ka,
Uh-huh.
and
Right.
then we found the effective resistance.
Effective resistance. Yes.
So
What
can you
next?
change the page?
Yeah, yeah, I have. Yeah.
Yeah, yeah. Uh, so we found the effective resistance, and then uh, uh, there is a heat distribution at the point B, and it reunites at point C. So
Absolutely
uh,
correct.
it's
Right.
like it's like delta theta net by effective resistance is equal to delta theta by R naught plus delta theta by R1.
Why did
R
we do
naught is
this?
the
Karuna, why did we do this step? Tell this to the class. What was the purpose and why is it applicable here? Both. What was the purpose
yeah,
to write this expression? To get a relation between temperature difference, right? We have a relation between heat current. So this is a relation between heat current, right? Between heat currents. What is it, Karuna? Heat current or electrical current?
heat current.
Heat current.
Hey,
So
heat
we have
current, sir.
right. So
Yeah,
we have a relation between heat current, but we are converting it into the relation between temperature differences, right? Because we were
yeah.
given with one temperature difference, that is that between A and D, and we were supposed to find out the temperature difference between B and C, right, Karuna? So this is the
Yes, sir.
purpose. This is the purpose. And why is it applicable here? Because from the figure, it can be clearly seen that it is the current I which is getting distributed into I naught and I1, right? Because this is clearly understood in the given question, we were able to apply it over here. Are we clear with this, Karuna, completely?
Yes, sir.
Okay, great, great. Thank you, class. Let us take the next question then. In case everyone is clear, please raise your hand. Yes, class. Okay, great. You can bring your hands down, everyone. Thank you. So we have next question. See here, everyone. We have next question given as we have again it is a rod based system. I think I've given quite similar number of similar pattern based questions in this. So we have again three rods, right, which are arranged in this pattern, right? Here we have length is 2L, this length is L, this length is also L. Their conductivities are A. Sorry, their conductivities are K, 2K, and 2K respectively. Okay. Their cross section areas are A, and A respectively. Okay, cross section areas are same. All right. Now, what is being told here, we have been given with temperatures. So this is 500 degrees Celsius. Okay. And at one end, at the right end, the temperatures are given as 0 degrees Celsius, right? Now, what is being told? We are being told that find the temperature of the junction T. Find the temperature of the junction T. Okay. So, Samriddhi, is your mic working? Can you suggest the solution for this question? Yes, Samriddhi.
Yes, sir.
Yeah. How do we go about this question, Samriddhi? Any ideas?
Uh,
We need to find out the temperature of the junction. Let's say I am naming the points as, let's say this is point A, right? This is point A. This is point B here. This is point C over here, and this is point D. So we need to find out what is the temperature of the junction D. Yeah. Any hints on this, Samriddhi? Can you explain the class or give us a quick approach how to approach this question? Yes, Karuna. Yes, Samriddhi.
so the temperature, the heat flow from the higher temperature to the lower temperature.
Yes, yes.
So,
So can we convert this in terms of
so
resistance diagram, Karuna? Samriddhi first, right?
yes, sir.
Okay, so let's do that. We will convert this into the resistance diagram, right? So if this is 500, right, this is 0, this one is also 0 degree Celsius, right? Now what should be happening here? Yes, Samriddhi.
So the resistance should be 2R.
Okay, so let us find out the resistances. Okay, great, great. So we'll have, that's a good approach, Samriddhi. We'll find out their resistances. If this is R, what is R given by, Samriddhi? L by Ka, right? What is the
Yes,
value of K here? So here L is 2L. Instead of length, we'll write 2L. Length upon 2, length upon K times of, or
K.
conductivity times of area. So here length is 2L, right? Area is A, conductivity is K. What about this resistance? Yes,
L upon 2Ka.
2Ka. Okay. How about this one? Same,
Yes,
L by
R is equals to
2Ka.
L upon 2Ka.
Right. So let us substitute these values somewhere. How do we do it? How should we arrange resistances now? Are, which one are in parallel, which is in series? Can you tell us? Yes.
Uh, 5 with the fire A,
Let's say this
A
is
to D.
R1. Let's say this is, I'll just name them, right? So let's say this is um, this one is R1, this one is R2, while this one is R3. Yes. Now tell me.
So the R2 and R3 will be parallel,
Sure.
and R1
How will they be parallel? Just tell us. Why will they be parallel? Yeah.
because current flowing will be divided through them.
Divided, but is it coming back again? I to see the current is going here and some part of the current is going here. How are they in parallel?
But the final temperature will be same. So
Because we see that the final temperature of both other end of R2 and R3 is 0 degrees Celsius. So we can assume that they are connected at this final junction, right? So basically the junction B and C are nothing but same junctions, right? B and C are nothing but the same junctions because the temperature at that point B and C is same. That is an excellent approach, Samriddhi. right? So let us go for it. Let us go for it, right? So now let's say if we take R1 as R, right? If we take R1 as nothing but R, how much should be R3 and R4? If this is 2, right? This is 2, this is 1, and this is 1 by 2. That means this is 1/4 of R, right, Samriddhi?
Yes.
Clear, no? That if R1 is
Yes.
equal to R, so these values R2 and R3 are 1/4 of R1, right? Because half is 1/4 of 2, correct?
Yes.
So we can write these expressions as, these resistors as, if this is R, this will be R by 4, this will also be R by 4, giving us the equivalent resistance circuit as R by 8 R. Then similarly this one will be 1 plus 1 by 8, that is 9 by 8, right, into R.
Yes.
Right, Samriddhi, are we clear on this?
Yes.
So this is the value of R effective. Am I correct, Samriddhi?
Yes, sir.
Okay, so we have R effective given as 9 R by 8. What next? What next can we do? Yes, Samriddhi.
Sir, R is equals to.
We can talk about that, like last time what did we do, Samriddhi? We talked about distribution of current, right? Distribution of
Yes.
current. Can we talk
Correct.
about distribution of current in this question?
Yes.
Okay, talk about it. Yes, tell us.
So I1 is equals to I2 plus I3.
What is I1? Let's say I1 is the current flowing through initial point
R1.
A, right? Or R1, right? So that I1 is distributing to I2 and I3, right? Where what is I2? I2 is the current through R2, and I3 is the current through R3, right?
R. Yes.
Okay. So therefore we have I1 is equal to I2 plus I3, right, Samriddhi?
Yes.
Now, how do you relate the heat current and temperature difference? Samriddhi, tell us.
So I is equals to delta theta by R.
So we have R is equal to delta theta upon R. What is R? L by Ka, right? Let us take this as R only this time because we have clearly all the other resistances in forms of R. Okay. So I1 is basically, let's say if this temperature is T, this one is 500. So this time we can give I1 in terms of both. We can give I1 in terms of 500 and 0, as well as we can give I1 in terms of A and D, right?
500.
Temperatures at A and D. So this is A, this is D, this is B, and this is C, right? So let us take I1. So I1 is not the net current this time, right? I1 is not the net current this time, right? I1 is, or maybe we can call it the net current also. Let us see how can we go about this question. So I think Atul wants to say something. Yes, Atul, tell us.
Sir, the resistance of the parallel combination should be R by 4.
So we'll check it. No worries. Yeah. Tell me. Yeah. See here. So here, if the resistance is 2L by Ka, right? Here the resistance is L by 2 Ka. So I have tried to write that if this is R, this will be R by 4,
R, okay.
and this will be R by 4,
Yes, sir.
right? So if you
Yeah.
have R by 4 and R by 4 connected in parallel, the net should be R by 8. Shouldn't it be, Atul?
R by 4.
Yes, Atul.
Waits.
Let me know. Yeah. Is there something you want me to add or subtract? Yes. Tell me.
Oh, no, no, sir. Yes, sir. Right, sir. Right, sir.
right? Okay, okay, great,
Yes.
great. All right.
I was adding them up.
Yeah, 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 that's okay. That's okay. I think we are clear with it, right? That we need to take them
Yes,
in
sir.
parallel. So the point is here, Atul, it's a good question that you have raised. Sometimes it happens that when we are doing calculation, we forget one thing, that whenever we have two resistors in parallel, right? And suppose they are same in magnitude, let's say both are R. So the net should be R by 2, right, Atul?
Yes, sir.
All right, okay. So we'll apply the same funda here, right? We'll apply the same funda here. So we will have, therefore, Acha class, about this question, I had taken that this I is equal to delta theta net upon, that is delta AD, right? I am little dubious on this because so dear class, I think the network got lost, so the connection is not that clear. I just wanted to clarify one thing, that in the diagram which we were drawing, right, there might be a correction. I will get back to you with the same. So this is, I think, if in case I don't, I think this will be the right method. So in the question where we had this kind of arrangement, right, and we are talking about this I, right, I which is going from the part R1, right? So I think then we can actually take that I is depending upon this temperature difference, that is between, if this was A, this was B, this was C, this was D, this was E, and this was F. So we can take that I is directly proportional to temperature difference between AB. Rather than taking it as temperature difference between AD, we can take that I is proportional to temperature difference between AB, right? And then what will change is we can write that I is equal to delta theta AB whole by R1. This can also be written in, or we can also write I is equal to delta theta AD upon R effective. Class, is the point clear? That what I'm trying to say, that if I is the current which is flowing in the circuit, right, if we can also call it as total effective resistance, right, whole by total effective total temperature difference whole by effective resistance, or just the temperature difference A and B upon the resistance between A and B, right? So that is how we could also have solved this question. So that question could have been solved in two ways. Both ways we'll get the same answer. If you all wish, please do try and verify and let me know in the evening class if you're getting the same. So I'll repeat what I'm saying. Today we have, in the question we adopted this approach. Try adopting this one, right, also, and see if you get the same answer or not, right? Just let me know in the evening class, right? Now the question which we were solving, let me tell in brief. So we had two resistances this way, right? We had resistances as R by 4 and R by 4, right? Then, so these are basically metal rods which we were assuming to be resistors, and then we wrote that these two are actually connected in parallel because the end temperatures were same, right? Here also the initial temperatures were same, let's say T. Here also this temperature is given as, I think in the question it was, yeah, I think it was 500. Okay, so this was 500, so we'll write this as 500, right? And these two resistors, right, they were in parallel, R by 4 and R by 4. This was R and this was 0. So we came to an understanding that we can write this as R and R by 8, right, which is nothing but 9R by 8 connected between temperatures 500 and 0, right? So this will be the total current I which is entering this, right? This will be the total current I, which will be entering this, which will pass through R, and then it will get distributed in these two circuits, in these two resistors, right? And then it will reach the zero end, right? So this current is not the electrical current class, this is thermal current. So we were told that find out what is the temperature T. This temperature T had to be found out, right? So Samriddhi suggested at a way that, sir, we can take, let's say I2 current is flowing here, I3 current is flowing here, and this is I1, right? So we could write, therefore, I1 is equal to I2 plus I3. Once we have this expression, we can use the expression for heat current, that is H is equal to Ka delta theta upon L, which is nothing but heat current is equal to delta theta upon R. So this is very close to what we read in current electricity, that I is equal to V by R or delta V by R, where delta V is potential difference. Here, delta theta is temperature difference. And class, very important that we get that delta theta is basically heat difference or temperature difference, and this is heat current, whereas this is electrical current. So why is this analogy happening? Because we know that electrical current flows because of potential difference, whereas heat current flows because of temperature difference. This is the beautiful analogy that we can have, right? Now let us substitute the values of currents, that is I1, I2 and I3, right? I1 will be given in terms of, see from the figure class, I1 will be given in terms of temperatures, higher to lower temperature. So we can write this as delta theta or 500 minus T, right? Higher minus lower, whole by R. Let's take this as R only. I2 will be equal to, what will be the temperature difference? Higher minus lower, T minus 0, right? And what is the resistor or resistance? R by 4. Then for I3, temperature difference is again T minus 0 upon resistance is R by 4, right? So we'll have this as, so we'll have this expression given as 500 minus T, right? Whole by, what is the resistance? R, right? R whole is equal to T minus 0 or just T upon R by 4, similarly plus T minus 0 or T whole by R by 4. So this is giving us 500 minus T, right, is equal to 4 plus 4 T, right? R and R gets cancelled on both sides. We have R and R here, which gets cancelled, right? And therefore we have this as 8T, right, plus T is equal to 500. Therefore 90 is equal to 500. Therefore T is equal to 500 by 9. All right. So Samriddhi, are we correct in this approach? Can you please verify and tell us?
Yes, sir.
Sure.
Yes.
Right? Okay. So class, we'll also try to solve it in the other way, as I just told. In the last question, instead of taking 500 minus T, what did I take? I taken 500 minus 0, right? And also I taken the effective resistance. Let's try doing that here, right? So suppose we have, why did we calculate effective resistance, right? It must be for some reason. So that is the reason. Let's try doing it and let's see if we get the correct answer. What I'm doing, in the expression for I1, right? In the expression for I1, what did we take last time? We had taken it as 500 minus T upon R. This time I'm taking I1 is equal to 500 minus 0 upon R effective. Let's see if we get the same answer or not, right? So let's try to validate this, and the answer should be same automatically. I1 value comes out to be same. Let's see if it does, right? So I1 we got as 500 minus T by R, right? we I am saying that we can also take I1 is equal to 500 minus 0 upon R effective. That is the total temperature difference upon total R effective. Let's see if the answers come same in both cases. So we have 500 minus T. We got T as 500 by 9, right, whole by R. So this is basically 8 by 9 into 500. Okay, let's see if we get the same value of heat current here. So we have 500 upon R effective, right? R effective came out to be 9R by 8. 9R by 8. Okay, so we get this as again 8 by 9. I think this was R here. I'll allow it to be, yeah, 500 into 8 by 9. Yes, absolutely correct. So class, are you trying to see what did I do here? Atul, can you explain what is the thing that I was trying and I got the success in it? Yes, Atul, can you try explaining? Yeah.
So the current flowing through AD, huh? So the current flowing through AD is equal to the effective current, total current, because they are in series, I think.
Right. So basically the entire expression, so see here class, what did I do? Instead of taking, for calculating I1, that is current through R1, instead of taking the terminal temperature difference, like this temperature difference, this one. Have a look here class, I'll draw it maybe in blue. Instead of taking temperature difference as 500 minus T upon R, right? I can also take, in order to calculate I1, as 500 minus 0, but then I'll have to take the entire effective resistance R effective. See, I changed this minus T to minus 0. So I also changed R to R effective. Are you able to comprehend this class? So this is what is also giving me the total current, because I1 or I is the total current in the circuit, which is actually getting split into two parts, I2 and I3, as Samriddhi suggested. Samriddhi, are you clear with this? Karuna, are you clear with this?
Yes, sir.
Karuna, are you clear with it?
Yes,
You can
yes.
ask me if you are not. What did I do? In order to find out I1, I can have two expressions. One expression can be temperature difference between the two ends of the resistor R, that is 500 and T, the difference between the two upon R. This is one way. Second way is that I am assuming that I1 is nothing but equal to the total current which is flowing between the ends 500 and 0, and in between there is R effective, right? So there are two ways of solving the same question, of writing the same value of I in two ways, right? Is everybody clear with the approach? In case yes, please raise your hand. I can write I1 in two ways. It can be written in terms of temperature difference between the 2 points of the resistors, and it can also be written as temperature difference between the entire circuit and the effective resistance. Temperature difference between the entire circuit and the effective resistance, right? And here temperature difference between just one resistor and its resistance. This is how I can write I1, because I1 is nothing but the total current in the circuit. Absolutely correct approach and explanation, Atul. Great. Okay, so I think all of you are clear with it. So I think we had two more questions. Let's finish them quickly, right? And let us be done with it, because next class then we can have some more understanding of KTG and its assignments. Okay, all right. So class, here we have, uh, so Karuna, can you read the question for us? Yes.
Yes. A body is cooling down in atmosphere according to Newton's law of cooling.
Okay.
If T is its instantaneous absolute temperature and T is time,
Mm-hmm.
there are graphs given.
Mm-hmm.
We have to choose one of the graphs.
Okay, can you briefly explain what is Newton's law of cooling in one line?
Yeah, one second.
It says that it's very simple. It says that the rate of fall of temperature is directly proportional to temperature difference between surrounding and the body which is cooling down. Are we clear with this, Karuna?
Yes, sir.
Repeat it. Yes, see your notes. No worries. Just repeat it. Yeah, tell me.
Temperature difference between
No, no. The rate of fall
uh,
of temperature or rate of cooling, right? That is
yeah.
d theta by dt, or rate of change of temperature. How fast is the temperature falling? That fall of temperature is proportional to, let's say, a body at temperature T, surrounding is at temperature T naught. The heat is coming out of the body, right? So as the heat is coming out of the body and the body is cooling down, the rate of fall of temperature of the body is dependent on the temperature difference between the body and the surroundings. Are we clear now, Karuna?
Yes, sir.
We
Yes.
need to write, or we need to plot a graph between log of this temperature of the body, natural log, and the time. Right? This is what we need to do. Are we clear now, Karuna?
Yes, sir.
Okay. So we will have this dt by dt is equal to, see there is a minus sign and I'm transferring it on the other side with a constant. I'm replacing proportionality with equal to sign. So it will bring a constant in the equation. Let me bring similar variables together like always before we perform integration. We had learned this formula. Karuna, do you remember in one of the previous classes that in such questions, how do you perform integration, right? We bring similar variables together. Do you remember, Karuna?
Yes, sir.
Okay.
Yes, sir. Yes.
Great. So let's say initial temperature of the body at time t is equal to 0 is, let's say, theta, right? Or we'll say, let's say it was final temperature is theta naught. It becomes same, or t naught, that is same as the temperature of the surrounding. I'll repeat, class, what I'm saying. The body is cooling. Suppose you have a cup of tea, right? Cup of tea. Atul, can you answer me if the temperature of the surrounding if the temperature of the surrounding is, let's say, 25 degrees Celsius, right? And the cup of tea when it was brought to you was 70 degrees Celsius. What will be the final temperature of the cup of tea if it is kept in
70.
final temperature?
70 minus 25.
No, no, no. Think again. Think again. सो अगर मैं हिंदी में कहूं कि हमने चाय का कप रख दिया, ठीक है, और वो आपने सुबह चाय दी आपको, लेकिन वो चाय शाम तक आपने पी ही नहीं, वैसी की वैसी ही थी until the evening. So what will happen in that case, Atul? If you didn't drink your tea until the night, what will be the temperature of the tea? Will it be same as surrounding?
25
Will it
degrees Celsius.
Yeah, yeah, tell me.
Yes, sir. So it will be same as the surrounding temperature.
Same as the surrounding, right? So initially, whatever
Surrounding.
the temperature was, finally at final time, the temperature will tend to become equal as that of
Temperature of the surrounding.
temperature of the surrounding. Are we clear with this, Atul? Very clear with this?
Yes, sir.
Okay,
Yes, sir.
right. So we can say that finally the temperature will become same as that of the surroundings. Let's say this is T. Initially, let's say temperature was, we can take this as, let's say this was T initial, this was T fine, this is the final. Let's say at some random time T, the temperature is capital T. So what are we going to do? Yes, Atul, can you tell me what should be the integral of 1 by T minus T naught?
1 by t minus t naught. We can write it as t minus t naught to the power minus 1.
Have a look. This is ax plus b form. Integral of dx by ax plus b. How much is it? Log of ax plus b whole by,
Log of ax plus b by whole by a.
right? So in this question, all we have is x is equal to capital T, right? Equal to
Yes, sir. Yes,
minus
sir.
T naught and A is equal to 1. Are we clear with the analogy, Atul?
Yes, sir.
Right. So what should be the integral? Tell me. Log of,
Log t minus t naught by 1.
absolutely correct. Absolutely correct. Very good, Atul. So here we'll have on the other side kt, right? Because integral of 1 is t, right? Now We can take the
Mm,
limits from 0 to t. Initially, let's say the temperature of the body was Ti, and from there it is going to T, right? Let's say its temperature was Ti initially, and at any given time, small t, its temperature is capital T, right? So how will we have the expression? We'll have the expression as log of T minus T naught, taking the limits from Ti to T is equal to minus K, T minus 0. Let's apply the limits. So we'll have log of, right,
T minus T naught
minus T
minus
naught, right, whole minus log of Ti
T1 minus T naught.
minus,
Ti minus T naught.
right, this is equal to minus Kt. Can we write it this way, Atul?
Yes, sir. Yes, sir.
Okay, now Atul, this temperature Ti is a constant value of temperature, right? Right?
Yes, sir.
What is T naught? What is T naught? T naught is the ambient temperature. T naught is the ambient or surrounding
Ambient temperature.
temperature, right?
Surrounding temperature.
Right.
Yes, sir.
And T is the temperature of the body, instantaneous temperature of the body, correct?
Yes, sir.
So this Ti is the initial temperature of the body. T naught is some temperature of the body, some temperature of the surroundings. So can we take this as some constant K naught? Yes.
Okay, it is constant. So,
So this is
yes, sir.
some
Yes, sir.
constant. So now, right? So we
Yes,
can
sir.
take this as log of T minus T naught minus of K naught is equal to minus KT. Can we write it this way?
Yes, sir.
Right. So we will have this as, pardon me class, this is actually expression between log of T minus T naught and T, right? We are being asked this expression. So this will become
Log
minus KT plus K naught, right?
K. Yes, sir.
Right. Now, can you try to connect and tell me, Atul, what should the equation look like? Equation between log of T minus T naught and small time t. Yes, Atul, get going. Right.
We will compare it to the equation y equals to mx plus c. So
Absolutely.
here ms,
Yeah, yeah. Go ahead. Go ahead.
mm,
Y is equal.
here ms minus k. Here ms minus k negative. It is a negative slope, so it will be a decreasing curve.
Very good. Very good. It will be a decreasing curve or a falling line, right? Do you remember this?
Yes, sir.
Atul? We had done rising line and falling line. We were when we were doing the basics of mathematics or
Uh,
mathematical tools of physics. Do you
yes, sir.
remember this, right?
Yes, sir. Yes, sir.
And the value of c, that is the y-intercept, will be given as, yes, tell me,
Y-intercept is k.
k naught, right? See here,
K naught. Yes,
right?
sir.
And what is k naught in our question? Log of ti minus t naught, right?
Yes, sir.
And
Yes, sir.
what do we call c? C is y-intercept, right? That is this value. Have a look.
Yes, sir.
This is c,
Yes, sir.
right? And this value,
Mm.
that means this part will be given as log of ti minus t.
Ti minus T naught.
Absolutely, because we can clearly see that here this is the graph between log of T minus T naught, where T naught is telling me instantaneous temperature. So at T is equal to 0, I have the body temperature equal to Ti, and therefore instead of Ti, instead of T, it should be a Ti value here. It's very evident, right? So we have the slope,
Yes, sir.
so we have the intercept, that is C, given as log of Ti minus T naught, right? And the slope of the graph is equal to minus K,
Uh,
right?
yes, sir.
And it is a falling line. So which one should be a correct option? I think we have four options, right?
Second.
The second one
Yes.
is correct, right? Absolutely correct. Absolutely
Yes,
correct.
sir.
Great. So class, if this approach is clear to you, how have I converted the expression, initial expression of Newton's law of cooling, this one, into the final expression between log of temperature difference and time? If this approach is clear to you, please raise your hand. Yes, class. Okay, okay, great. So thank you everyone. Thank you for being a part of the class today. Let us take one more question in the class in the afternoon, right? And the concepts of KTG. there itself, right? So I'll send you some questions on KTG, try solving them, and we'll take those some concepts, right? And some concepts and the questions in the evening class, right? Thank you everyone for being a part of the session. Let us meet in the next session and discuss kinetic theory of gases and some assignment questions based on that. Thank you, class. Thank you.
Thank you, sir.
Thank you.